Hello, welcome to section 6. This section we are going to continue talking about operations with matrices. Remember in the last section we talked about adding and subtracting matrices, and we talked about scalar multiplication, which is multiplying a matrix by a number. What we're going to talk about today is actually multiplying two matrices together, and this process is a little bit different. You don't just multiply corresponding elements, there's a different process for multiplying matrices. That's why it gets its own section. Alright, so when I multiply matrices, I have to know the dimensions. The dimensions are 100% important to figure out whether or not you can even multiply two matrices together. So this says you can multiply two matrices, A and B, if and only if the number of columns in A, so that would be this part of the dimension here, the number of columns in A, is equal to the number of rows in matrix B. When I do that, so these two inner dimensions, we call them, sometimes have to match. The number of columns in A has to match the number of rows in B. My result, when I find A times B, my resulting matrix will have the dimensions of M and T, meaning it will have the number of rows in A and the number of columns in B. So my two middle dimensions have to match, and my result, my answer, will have the dimensions of M and T. So let's look at what that would look like. So here I have two matrices. I have matrix A, which is 3 by 4, and matrix B, which is 4 by 2. So first of all, determine whether the product is defined. That means, can I multiply it or not? And if it is, what are the dimensions of the product? What are the dimensions of the result? So in this case, A is 3 by 4 and B is 4 by 2. My inner dimensions match, so these two 4's match. There we go. So since these 4's match the number of columns in A and the number of rows in B, that means yes, I can multiply. And my result, A times B, will have the dimensions of 3 by 2, taking the number of rows from A and the number of columns from B. So when I multiply, I would get a 3 by 2 matrix, which we're going to practice here in a minute. Okay, here I have a 3 by 2 matrix and a 4 by 3 matrix. In this case, my product is not defined because my inner dimensions, the number of columns in A and the number of rows in B, do not match. So my product is not defined, so I can't say what its resulting dimensions will be because I can't even multiply it in the first place. All right, you guys try this one. This one should be 3 by 3 because these inner dimensions here match. And try this one. This one is not defined, which seems weird because both of these matrices are the same size. They're both 2 by 3. But I cannot multiply them together because the number of columns in A is not equal to the number of rows in B. And we're going to see why that's important now. Okay, when I multiply matrices, basically what I have to do is multiply the rows in A times the columns in B. So look over here. My first element in my product, in my result, is AE plus BG. So that comes from the first row of A and the first column of B. And what I do is I take A times E, that goes here, plus B times G. And that goes here. That gives me my first number. Then I repeat and I do the first row, second column, and that's going to go in the first row and second column of my resulting matrix. So I do A times F, that's right here, plus B times H. And then I'm going to do the same thing but with the second row. So I'm going to do the second row times the first column and times the second column. So I'll do C times E plus D times G. Then I will do C times F plus D times H. And that will give me 4 elements here because both of these matrices are 2 by 2. So my inner dimensions match, so I'm allowed to multiply. My outer dimensions are 2 by 2, which give me the dimensions of my answer, of my result. Okay, so let's try one. We're going to find R times S. So we're going to get a new matrix, R times S, if R is this matrix and S is this matrix. So we're going to write them out, and then we're going to start our process. So I'm going to multiply the numbers in my first row of R. Remember, this is matrix R, this is matrix S. First row of R times first column of S, add the products, and put it in my new matrix. Okay, so look what we did here. We did the first row, 3 and 2 times negative 2 and 1. So I do 3 times negative 2 plus 2 times 1. Then I'm going to do the same thing with the first row, second column. So I'm going to do 3 and 2 times 1 and negative 1. 3 times 1 plus 2 times negative 1. Then we're going to repeat that process, but with the second row. So here I'm going to do my second row, first column, negative 1 times negative 2 plus 0 times 1. And then I'm going to do second row, second column. Negative 1 times 1 plus 0 times negative 1. So I have this matrix full of these products and sums, and then I just have to simplify. So this becomes negative 6 plus 2, which is negative 4. 3 plus negative 2, which is 1. 2 plus 0, which is 2. Negative 1 plus 0, which is negative 1. So my final answer, RS, is negative 4, 1, 2, negative 1. Okay, I want you guys to try that. Multiply this R and this S and get the resulting matrix. Okay, you should have gotten D. And here's the process for that multiplication if you need to look over how we got from here to here. Okay, here we have a real-world example, and we're going to multiply matrices that are not just 2 by 2, which is important to practice. So here we have 3 teams, the blue, red, and green team that competed in a chess club championship. For each win, a team was awarded 3 points, and for each draw, 1 point. So here's the number of wins and draws that each team had. So we're going to arrange this information into a matrix to answer the question, into 2 matrices actually, which team won the tournament. So we're going to multiply the number of wins and the number of draws by the points for each one so that we can figure out the final answer. So we're going to start by writing our matrices. Here's our results matrix, right? We're setting up the matrices so that the number of rows in my points matrix, so 2 rows, is equal to the number of columns in my results matrix. Why? Because when I do row times column, I need to have the same number. So I need to have, if I have 2 elements in this row, I need to have 2 elements in this column. So these are the results for each of my teams. Each row represents 1 team, and this is the number of wins and draws. And then here are the points, 3 points for a win and 1 point for a draw. That's going to work because here I'm going to do 5 wins times 3 points plus 4 draws times 1 point. So now we're going to multiply these matrices together, and we're going to do the same process. So I'm going to do the first row times the first column, 5 times 3 plus 4 times 1, and that goes right here. Notice that this matrix is 3 by 2, this matrix is 2 by 1, so I'm allowed to multiply because my inner dimensions match. My resulting dimensions will be 3 by 1, so I'm going to have 3 rows, but only 1 column. There's not a second column in my matrix here to multiply by, so I move on to the second row times this column. So 6 times 3 plus 3 times 1, that goes right here. And then I'm going to do my third row times this column, 4 times 3 plus 5 times 1, and that goes right here. Then we just simplify that, and my final answer is a 3 by 1 matrix, 3 rows, 1 column. So remember that each row represents a team. So the blue team, the red team, and the green team got this many points. That means that the red team won the tournament because they had the most points out of everybody. All right, you guys try this one. Okay, your answer should be C, Chris. Okay, here's what your matrices should have looked like for this one. Chris ends up being the winner. Your first matrix is a 3 by 3 matrix, 3 rows, 3 columns, that list out the number of shots that the people made who played basketball. So Wharton made 2 free throws, 3 2-points, and 2 3-point shots, for example. All of that information is in this matrix. And then it tells me that they get 1 point for the free throws, so that 1 is going to have to be multiplied by the things in the first column. 2 points for a 2-point shot, imagine that, and 3 points for a 3-point shot. So when I multiply, I'm going to multiply row by column, and I will be multiplying and adding correctly. So I'll take the number of free throws times the points for free throws, plus the number of 2-point shots times 2 points, and so on. So your answer should have given you Chris as the winner. Okay, notice here the title of this example is Testing the Commutative Property. So we're going to see if the commutative property is true for matrix multiplication. So here I'm going to multiply k times L, so k first and L second. When I do that, that works because this is a 2 by 3 matrix and this is a 3 by 2 matrix. I'm allowed to multiply because I have 3 elements in my row and 3 elements in my column that will match up. So when I do my multiplying, I will multiply the first row times the first column, so -3 times 1, which is -3, 2 times 4, which is 8, 2 times 0, which is 0, and I add all of those together to get 5. Then I'm going to do the first row, second column. -3 times -2 is 6. 2 times 3 is 6. 2 times -1 is -2. Add those together to get 10. So those are my first 2. Then I'm going to do the second row times the first column. That gives me -9. And the second row times the second column gives me -4. So this is my final matrix. This is K times L. 5, 10, -9, -4. So what we're going to do next is we are going to try the other direction, L times K, because remember the commutative property for real numbers says that 3 times 2 will give you 6, and if I change the order and do 2 times 3, I'm still going to get 6. So we're going to see if this works for matrices. So I'm going to do L times K. L is a 3 by 2 matrix, and K is a 2 by 3. So I'm allowed to multiply these. My result is going to be 3 by 3. So you can already tell the result of our last one was 2 by 2. The result of our new one is going to be 3 by 3. So you can already tell they're not going to be equal. Oops, sorry, didn't mean to go on yet. So I'm going to do my multiplication. First row times the first column, that goes here. First row times the second column, that goes here. First row times the third column, that goes here. And remember when I say times the column, I'm talking about the first element here times the first element here plus the second element here times the second element here. So we're multiplying and adding. Then we would do second row, first column, second row, second column, second row, third column, and repeat with the third row. So I'm going to multiply all of these. There's my last row. There's my second row. Okay. And we simplify, and we're going to get a 3 by 3 matrix, which is this. This matrix is not equal to the matrix we got when we did K times L. Here I got a 2 by 2 matrix. Here I got a 3 by 3 matrix, and they are not the same. Matrix multiplication is not commutative. So that means that it changes depending on the order that I multiply my matrices in. So you cannot assume that just switching the order means that you will get the same answer. So let's try this. You're going to do A times B. And you should have gotten B, 3, 0, 6, 3. And B times A, which gives you 3, 2, 0, 3. So notice again, A times B was not the same as B times A. So to finish up this section, this is just a reminder of some of the properties of multiplication for matrices. Matrix multiplication is associative as long as the matrix order doesn't change. Scalar multiplication is associative, and I can distribute matrices from the left and right, but I cannot use the commutative property. So all of these properties are true.